Right at the very heart of how our universe works, there's this contradiction. It's so strange it seems totally impossible. It turns out that the fundamental building blocks of our reality, things like light and electrons, can act like two completely different things at the exact same time. So welcome to the quantum riddle of wave-particle duality. Okay, so let's get our heads around this. In our everyday world, things are pretty simple, right? You've got particles, think of them like tiny little bullets. They're in one specific place, they follow a clear path. Then you've got waves, like ripples in a pond. They're spread out, they don't really have a single location, and they create these cool interference patterns. They are complete opposites. I mean, classically, something just can't be both. And this leads us to the central mystery. If the building blocks of everything aren't just particles, and they aren't just waves, what are they? What is this stuff really made of? That's the big question we're going to unpack in this explainer. Our story really kicks off with a debate that raged for hundreds of years, all centered on something we take for granted every single day: light. For centuries, some of the greatest scientific minds just went back and forth on this. You had Newton, who was firmly on team particle, then you had Huygens, who was team wave, and then in 1801, an experiment by Thomas Young seemed to settle it for good. He showed light creating interference patterns, which is classic wave behavior. So, case closed, right? Well, for about a century, yeah. But then a completely new experiment came along that wave theory just couldn't explain at all.
The thing that blew the case wide open again is called the photoelectric effect. And it sounds complicated, but the idea is simple. If you shine the right kind of light on a piece of metal, it literally kicks electrons out of it. But the details of how it does this, that's where things got really baffling for physicists.
See, if light were just a simple wave, then a brighter light, a more powerful wave, should have more energy to knock those electrons out, no matter what color it is. But that's not what happens. Not at all. You can blast a metal plate with incredibly bright red light, and absolutely nothing happens. But then you shine even a very faint blue light on it, and poof, electrons are ejected immediately. It was the color, the frequency, that mattered, not the brightness.
This whole puzzle led to one of Einstein's brilliant insights back in 1905. He proposed that light isn't some continuous wave. Instead, it arrives in these little individual energy packets, which we now call photons. A single photon of blue light has just enough punch to knock an electron out. A red photon doesn't. And it doesn't matter how many of those red photons you send. So just like that, light was a particle again.
So if a wave can act like a particle, could it work the other way around? Let's flip the script and look at the mystery of matter. I mean, surely something with mass, like an electron, is just a particle, right?
For decades, all the evidence pointed in one direction. We measured the electron's mass, we measured its charge. When we watched them fly through cloud chambers, they left these clean, particle-like tracks. I mean, everything we knew about them just screamed that they were tiny, solid little bits of matter. But then in 1924, a young physicist named Louis de Broglie made this absolutely wild suggestion in his PhD thesis. He basically asked, if waves can act like particles, could particles, like electrons, act like waves? It was a truly radical idea, one that just turned physics completely on its head. And believe it or not, just 3 years later, it was proven true. In a famous experiment at Bell Labs, scientists fired electrons at a crystal, and instead of just bouncing off like tiny bullets, the electrons created a diffraction pattern. That is the exact, unmistakable signature of a wave. Matter itself was a wave.
Okay, so now we have this crazy paradox. Light is both a wave and a particle. Matter is both a wave and a particle. And there's one single iconic experiment that brings this entire baffling contradiction into the sharpest possible focus.
The setup for this is beautifully simple. We take what's basically an electron gun, and we fire electrons one at a time towards a wall that has two very narrow slits in it. And behind that wall, there's a detector screen that just lights up wherever an electron hits.
So here is where the core paradox really smacks you in the face. If electrons were just simple particles, you'd expect to see two bright lines on the screen, right? One for each slit. But that is not what we get. What we actually see is a full-blown interference pattern. Lots of bands of hits and no hits. That's a result you can only get if a wave passed through both slits at once and interfered with itself.
But hold on. Remember, we are sending these electrons through one by one. Each electron still hits the screen as a single, indivisible little dot. It lands in one specific spot, exactly like a particle would.
And yet, as you let this run, As thousands of these individual particle-like dots build up, they slowly form that wave interference pattern. It's as if each individual electron somehow knows about both slits and the final pattern it's supposed to be a part of. And that is deeply, deeply strange.
So how is this even possible? How can one electron go through two places at once? Well, this is where we get to the most mind-bending part of this entire story.
So physicists, naturally, decided to cheat a little bit. They thought, okay, let's put a tiny detector right at the slits so we can peek and see which one each electron actually goes through. Does it go through the left slit or the right one?
And the moment we do that, the instant we try to observe the electron's path and pin it down as a particle, the wave behavior just disappears. The interference pattern completely vanishes, and we're left with just two simple bands, exactly like we were firing tiny bullets all along. The very act of looking, of measuring, forces the electron to pick a side and behave only like a particle.
Now, this isn't just some bizarre party trick. This duality, this quantum weirdness, it's the fundamental rule book for how reality works at the smallest scales. So what this all means is that an electron isn't really a particle that sometimes pretends to be a wave, or a wave that acts like a particle. No, it's a quantum object that holds the potential to be both, and which property it actually shows us depends entirely on how we choose to measure it.
And why does any of this matter to you? Well, because understanding this duality is the bedrock of all of quantum mechanics, which is hands down the most successful scientific theory in human history. It's the reason we have lasers, transistors, computer chips, M&I machines. Our entire modern technological world is built on this very paradox.
Which leaves us with one last really profound thought to chew on. If the fundamental nature of reality itself actually shifts based on whether or not we're observing it, what is the universe really like when no one is watching? And that is the quantum riddle that continues to fascinate scientists and philosophers to this very day.